I used to wonder if it's shorter to cut through the buildings or to walk around them. I mean, going like this is obviously longer than going like this, but what if you're actually going like this? If you add up all the segments of this path, you can see it's the same length as this path, but isn't it kind of closer to this path? So shouldn't it be kind of shorter? I've since concluded that in practice, it is kind of shorter to cut through the buildings because you're not turning in perfect right angles. Your path actually looks more like this, whereas you're kind of forced to turn a pretty much right angle if you go around. But screw practice. This is a math channel. So let's assume we are actually going in a perfectly right angled zigzag. But what if the buildings were smaller? And smaller? And smaller? At this point, you might be having a sense of deja vu if you tend to skulk around the interwebs for math things. But yeah, here's a proof that the square root of 2 equals 2. Here we have a right angle triangle. The length of these sides are 1, so by Pythagoras' theorem, this side must have length square root of 2. Length of these sides add up to 2. Now if we fold this corner in, we've got 4 lines of length a half, which still adds up to length 2. Fold all the corners in again, we get 8 lines of length a quarter, and so forth. No matter how many times you do this, the whole thing's still of length 2. But eventually you get this line, which is of length the square root of 2. Therefore, the square root of 2 equals 2. Just kidding, of course. If 2 is the square root of 2, then 2 times 2 must equal 2. But 2 times 2 is 4, and 4 is not 2. So the real conclusion is that everything we've been taught was a lie. This length isn't the square root of 2. It's 2! Sorry, I had to. But here's a proof that pi equals 4, using a similar argument. We get a circle of diameter 1, so the perimeter should be pi, and the perimeter of this here square should be 4. If we fold the corners of the square down to the circle, the perimeter should still be 4, and so on. Of course, we can show that these proofs lead to a contradiction without relying on Pythagoras. We can also fold these things down to the line and the circle respectively, which would mean 4 equals 2 and 6 equals 4. So where do these proofs go astray? Most people say it's because when you fold the zigzags down, you don't get the actual line or the circle, but rather a really crinkled thing that just looks like it. But you know what? That approach is too mainstream. Here's some axes. Now let's plop our triangle right here. Now we have the graphs of 2 functions. This one here, which would call f0, and this one here, which is just the constant function that's 0 everywhere. We'll call it 0 underscore. Now we add another function, f1, which is just f0 folded down to the x-axis, and f2, which is just f1 folded down to the x-axis, and so forth. Notice that for each function fn, the highest point is twice as high as the highest point of the next function, fn plus 1. Root 2 on 2, root 2 on 4, root 2 on 8, etc. In fact, the highest point for each fn is this thing here. Now, I propose that f infinity is exactly the 0 function. Here's the proof. Assume f infinity is not 0 at some point p. Say f infinity at p is a small positive number epsilon. But wait, this thing here can be smaller than epsilon if n was large enough, which means the highest point of f infinity, which is at least epsilon, is higher than the highest point of some function before it, which shouldn't happen. So f infinity must be 0 everywhere. But wait, if f infinity actually is the horizontal line, which has length square root of 2, but also has length 2, does the square root of 2 actually equal 2? Well, I wouldn't say f infinity has length 2. It's not like the other fn's. F infinity is the limit as n approaches infinity of fn, and by that we mean f infinity is the function that the sequence of fn's get closer and closer to. It seems reasonable to say a sequence of functions gn gets closer to a function g infinity if gn evaluated at each point p gets closer to g infinity at p. In this case, fn at every point gets closer to 0. It doesn't matter what distance epsilon you choose, there will always be some fn that's less than epsilon away from 0 at every point. So in that sense, the zero function is indeed the limit of the sequence of fn's. But let's now look at the limit of the sequence of the length of the fn's. It's 2's all the way down. It's not getting any closer to anything other than 2, so the limit is 2. But the length of the limit of the fn's is the square root of 2. So the limit of the length is not equal to the length of the limit. Is that really a problem? I mean, let's look at a completely different sequence. You might have heard of this sequence. Its limit is 2. Now let's make up an operator I, which takes the smallest integer that's larger than your number. So I of a half equals 1, I of 1 equals 2, I of pi equals 4, etc. Now, if we look at the sequence of I of the SNs, it's just a sequence of 2's, so the limit is 2. But I of the limit of the SNs is I of 2, which is 3. Again, the limit of the i's is not equal to I of the limit. Does it mean the limit of the SNs isn't 2? No, it just means taking limits doesn't preserve the I of a number, just like taking limits doesn't preserve the length of a line. If that example was a bit too artificial for you, consider this family of functions. Each member of this sequence is nice and continuous, but the limit looks like this. So taking the limit doesn't preserve continuity either. So I guess my point is, the zigzags are super crinkled versions of a line of length 2 at any finite step of the crinkling, but the limit of those zigzags at infinity is a genuinely straight line of length root 2. And all those folded down squares in the pi equals 4 proof are super crinkled shapes of perimeter 4 at any finite step, but the limit at infinity is a genuinely smooth circle of perimeter pi. The problem with the proofs is that they assume taking the limit of an infinite sequence of lines preserves length. But before anyone goes out to look for advocates of the crinkly zigzag theory and call them wrong, they might just be introducing you to an idea or exploring possible things that can follow if you assume it's valid, or only talking about approximations and not exact mathematical truths. For example, if you look at this video by Weihart, they wrote, "If this video was supposed to be teaching you, I'd probably have to make it boring and say that in one sense of limits, spoiler alert, you actually do approach a circle and a line, solving the apparent paradox by saying that the invariant of length does not hold over infinity. Luckily, I'm an artist and this is a rhapsody, and instead of learning, you get to actually think, if you like." While I usually agree with Weihart that this is the boring approach to things, well, I haven't seen anyone else make a video of it, so yeah, bye.